Hi, everyone. Welcome to this webinar on Inside AI Agents, what sets agentic systems apart. I'm your presenter, Puneet. The primary motivation for this talk was in my journey to educate myself about agents, I found there was a lot of information about the specifics of agents and how they operate, but not a lot about the bigger picture of when those systems add value to your system or product and the like. So here's my brief attempt to answer some of those questions. Who am I? I have 7 years of PM experience across Amazon, Cruise, and now at Cisco. I have experience in personalization, recommendation systems, the AV autonomy stack, and currently I'm working on something exciting at Cisco. I'm passionate about automation, especially cognitive task automation, as I like to term it. Two books I recommend everyone should read are The Beginning of Infinity and Engines That Move Markets. A quick look at the agenda for today. We will review the different parts that make up an agent, the agent anatomy. We'll review a view of the different components of an agentic system. And we'll also go through different vectors of a decision framework that hopefully helps product practitioners assess whether an agentic system will be valuable for them. All right, looking at the agent anatomy, there are 6 parts that we'll briefly go through: role and focus, tool use, memory, planning, collaboration, guardrails, and error handling. What is an agent? This is a very tricky question, but generally speaking, a system that is capable of executing long-running, open-ended tasks in complex, dynamic environments, ideally without critical errors. Generally, this means using, of course, an LLM, some tool usage, some semblance of memory, as well as planning. So let's start with role and focus. So this defines what our agent is designed to do and what it specializes in, the combination of role and focus. So role is, it defines what an agent is responsible for, and a task or a function that the agent performs. And focus is the scope of the agent's task. It is the depth and granularity of the task's execution. These define the agent's primary purpose and specialization, and they determine the scope of task and decision-making authority, and also guide the agent's action and priorities. As a simple real-world example, consider 3 AI agents, all with the role of a data analyst for a large e-commerce company, but each with a different focus, right? One can be a sales trend focused, another one can be customer behavior focused, and yet another one can be operational efficiency focused. So you can see, although the role is common, their focus is different. Okay, moving to tool use. At its core, tool use involves creating programmatic interfaces that allow AI agents to interact with external systems and services. This is typically implemented through function calling, where the agent can request specific actions or information retrieval from predefined tools. But what this generally requires is generating specific tool request strings, such as the one that you can see: tool, web search, query, coffee maker reviews. So it's not just about having access to these tools, but also about the agent's ability to reason about when and how to use these tools effectively. Key examples include web searches for up-to-date information, database queries for specific data retrieval, code execution for computational tasks, and so on and so forth. The benefits are, of course, agents can extend their capabilities far beyond just language processing. They can interact with real-world systems and complete complex multi-step tasks that require diverse actions. Challenge: agent needs, I'm sure you guys have used LLMs for using tools, and they're far from perfect. They need to select the right tools for each task, handle potential errors or unexpected outputs from these tools, and maintain context across multiple tool users to achieve coherent results. Moving on to memory. Memory is the ability of the agent to remember and recollect what it has done already, ideally learn from it and apply it to future executions. There are different types of memories: long-term, short-term, and entity. Short-term memory is the one that is retained during the execution of the task. This can be used to share knowledge, activities, and learning with other agents. within the context of a particular task. And they can share intermediate information even before task completion. Long-term memory, as the name suggests, it is stored after the execution of the current task as well. And this can be used in any future tasks. And it leads to sort of like self-improving agents. And then finally, entity memory. This can be either persons, organization, locations, and so on and so forth. Moving to planning. Planning is key for AI agents to accomplish complex tasks by breaking those down into smaller, manageable steps, right? LLMs autonomously decide the sequence of steps to accomplish those tasks. For example, an LLM can break down an online research task into smaller subtasks while researching subtopics, synthesizing findings, and compiling a report. This helps with complex task handling. Planning is essential for tasks that cannot be completed in a single step or with a single tool invocation. And while planning is powerful, it can lead to less predictable results compared to deterministic agentic workflows. And you'll hear this theme over and over again. Another issue is error handling. When configured in case of a basic search and answer type of task, if a particular website is down, the agent can pivot to use a Wikipedia search tool instead, completing the task successfully. So it gives you the option to try alternatives in case the happy path doesn't work. Moving on to multi-agent collaboration. This is a scenario where more than one agents work together to come up with better solutions than a single agent otherwise would. Multi-agent collaboration involves breaking down a complex task into subtasks executed by different agents with different roles and focus and other attributes that we have touched. Some of the benefits using multiple agents, even if they call the same LLM, has shown superior performance. An example is the LLM-based DBA or DBot, which has shown superior performance in diagnosing database-related issues. Long input contexts can be difficult for LLMs to handle effectively. So focusing on one task at a time improves performance. And then decomposing tasks into subtasks allows for better optimization and clarity in each role, of course, enhancing the overall efficiency. Some frameworks that are already in practical use, like AutoGen, I'm sure you heard of it, Crew AI, LangGraph, offer rich tools for building multi-agent solutions. There are a lot of collaboration models, sequential, hierarchical, hybrid, and I'm sure there will be a lot of permutations and combinations of these in the future as well. Finally, guardrails and error handling. They're like the safety training and emergency procedure for an agentic system. Guardrails are boundaries we set to keep our AI agent operating safely. AI guardrails prevent the agent from taking actions that could be harmful or inappropriate. Error handling is basically how our agent responds when something goes wrong. These features are crucial because they prevent the AI from causing harm, ensure the system remains stable, even in unforeseen circumstances, provides a safety net for autonomous operations. We'll come back to autonomous operations in a bit, and build trust by making AI system more reliable and predictable. Moving on to the agentic system components. So this view here is an attempt to show the different components or the layers of a mythical, fully agentic system end-to-end. The order is in terms of increasing complexity and at least currently decreasing manual intervention. Starting with the bottommost layer, with sensing, you want to monitor and gather relevant data from various sources. After you've done so, you want to reason, you want to analyze data and draw conclusions. Then you want to do some objective and trade-off evaluation, assess how potential actions align with business objectives or not. And one good example of it is Anthropic's constitutional AI, which aligns the models to abide by high-level normative principles written into a constitution. Then planning and execution, determine the best course of action based on the analysis that you've done and carry out the planned actions. And learning and improvement, evaluate the outcomes and update the strategies you've either assessed or executed for future tasks. The boundaries between these layers will likely blur to some degree. For example, React already merges reasoning and action, the framework. And Wave AI is, there's an end-to-end AI driving model from sensing to motion. and to a relatively lesser extent, mobilize RSS. Path to adoption. So this is just my personal take on what it will take for agents with these capabilities to become prevalent in the industry. The orange line shows the baseline quality, and the green shows the adoption threshold. And as you can see, the adoption threshold is higher for the more sophisticated agent capabilities. And the agent quality, the area under the curve, which represents the time and effort it will take to improve the agent quality to a level such that it reaches an acceptable level, increases with every step in the sequence. Just a mental map. All right. Now for the more interesting part of the talk, should one use agentic system or not? Like Hamlet, we are also pondering over that question. But before we start, some first principles. This wouldn't be a PM talk if we didn't mention some first principles. So here those are. Just a reminder, LLMs are probabilistic, semi-deterministic systems that generate contextually relevant outputs by predicting patterns in the training data. Generally, the training data is either natural languages or symbolic languages. Symbolic languages, example, mathematics or algebra. Natural languages are LLM's primary domain, but they can extend their functionalities to symbolic representations. And symbolic, there are a few symbolic language types. One is pattern-based and repetitive with predictable structures and clear patterns, examples being programming languages such as Python or SQL or JSON. Then there are rule-driven with dependencies where there are strict logical relationships, example, algebra, regex, Boolean logic, and the like. And then there are multi-step or hierarchical reasoning ones, which have sequential and layered logic. And examples are like compiler syntax. So there are three key questions, at least three key questions that we should keep in mind again when we're discussing the vectors. Can we rely on semi-deterministic, probabilistic outputs for a task? The second one being, can a deterministic system do a task without having to explicitly define every single combination? And the third one is, can we augment our current systems with generative capabilities? So key things to keep in mind: probabilistic, semi-deterministic systems, these are agents, or LLMs in general, which excel in natural language and with varying degrees in symbolic language. And we should compare and contrast with deterministic systems given a task or a system or a sequence of actions that need to be taken. All right, vector one, given a system or a task or a product or a service, I'll just use the word system. Does the system need to operate with high accuracy or low tolerance for error? So this is the vector of accuracy and risk tolerance. As I'm sure you'll predict that for tasks that need high accuracy, deterministic systems are more suitable, right? And for low-risk tasks, agentic systems can excel where minor errors are acceptable. They thrive in creative, low-risk tasks such as generating route alternatives that prioritize scenic views, even if they involve slight inaccuracies. And for context, the examples that I'll be using in the vectors are from the self-driving car industry because it's generally related to driving, and I hope they will be easily understandable. So again, examples of high accuracy, emergency braking to avoid collisions. We definitely don't want a probabilistic system, but if we have to generate scenic detours with minor route inaccuracies, we should definitely use a probabilistic system because it can help generate a lot of alternatives. So that's vector one. Does your task require a high degree of accuracy, and how much risk tolerance do you have? Vector two, variability of the decision environment. Does the system need to handle static versus dynamic, a lot of unpredictable scenarios or uncertainty? So in static environments, deterministic systems are effective in controlled environments like testing tracks where variables are predefined and predictable. But in dynamic scenarios, such as in real-world driving, these introduce unpredictable, complex variables that deterministic systems struggle to handle, especially because of the long tail, or rather, primarily because of the long tail, right? So remember I mentioned earlier, if deterministic systems can account for all the variables, they work quite as well, but the list tends to grow really, really long, and that's where they become a little less reliable. So example, a self-driving car navigating during a thunderstorm encounters flash floods, blocking several routes, and then there are live police manually redirecting traffic, and there can be accident-related congestion updates. In this case, unless the deterministic system already accounted for all of these, it's unlikely it will perform really well. But a properly configured agentic system can dynamically synthesize these diverse inputs and prioritize safety by avoiding flooded roads, complying with the police instructions, adjusting the routes, and so on and so forth, and perform the task really well. Why does this matter? Because dynamic environments require adaptability and multivariable reasoning, strengths that agentic systems have. Deterministic systems, again, they lack the flexibility unless each and every permutation and combination has been already accounted for to manage unstructured and evolving scenarios. All right, moving to vector 3, autonomy and goal directedness. Does the system need to autonomously set, modify, and pursue complex objectives? So we can think of this in terms of reactive behavior and a proactive behavior. Reactive behavior, aka deterministic systems, respond to specific inputs but lack the ability to rethink overarching objectives, whereas proactive systems can proactively modify objectives and strategies to meet broader goals. And just to take an example, let's say we have an autonomous delivery vehicle, and if one of the key routes is blocked, the non-agentic system will reroute us to get to the next destination. But a proactive behavior or an agentic system will not just reroute the car, but reanalyze the entire delivery schedule, identify which packages need prioritization, reschedule low priority deliveries, and optimize new routes to meet deadlines. So agentic systems excel in goal-oriented optimization, dynamically redefining objectives based on new inputs and evolving priorities. Which is to say, like, proactive autonomy is about goal adaptation, not just reacting to triggers, but rethinking the bigger picture to optimize outcomes. So again, if your system needs to autonomously assess how it's doing based on the overarching objective and adjust based on some inputs and environmental changes, one should consider an agentic system. Vector 4, strategic reasoning. And the question here is, does the system need to handle multi-step problems or evaluate long-term trade-offs, or even short-term trade-offs for that matter? So strategic thinking plans multi-step actions while accounting for dependencies and evolving priorities, and trade-offs balance long-term benefits, risk, and competing priorities dynamically. So why are the agentic systems might be good in these cases? So multi-step planning requires adaptive reasoning to handle interdependent actions. And for example, let's say we have an autonomous road clearing vehicle. So during a snowstorm, a self-driving snow clearing vehicle must decide the order of clearing routes, right? First, they must prioritize emergency routes, hospitals, fire stations, and the like, and then address main roads to reduce congestion, and then finally clear residential areas and the like. Deterministic systems will require rigid rules and can't adjust dynamically to changing priorities, such as sudden emergencies or weather intensification. In terms of trade-offs, trade-offs involve balancing the impact against the needs or the various needs of the ecosystem. For example, in extreme cold, a self-driving car must decide whether to take a longer detour to avoid icy routes. So short-term trade-off might be a detour increases battery usage and delays the current trip, but a long-term trade-off is that it prevents potential accidents, ensures passenger safety, and avoids system damage from icy terrain, right? So it has to consider all of those factors. So deterministic systems might follow pre-programmed rules for detours as well, but fail to evaluate the nuanced balance between immediate and long-term impacts. Finally, learning and adaptation. This maps really cleanly to the top of the pyramid that we had in the earlier slide. And the question here is, does the system need to improve performance over time and through experience? So deterministic systems rely on predefined rules. As I'm sure you all have experienced, they don't necessarily, quote unquote, learn at least autonomously. However, they cannot improve their behavior without explicit reprogramming. And an agentic system learns from historical data. An example can be recurring traffic surges during game nights and can adjust future routes proactively before congestion occurs. And unlike deterministic system, it improves performance through experience and anticipates congestion even when live traffic data is incomplete or delayed. And then contrast with deterministic system. Deterministic system might reroute when congestion is detected in real time, but cannot predict and adjust before the issue arises. So again, the question to ask here is, do we want our system to learn from the past experiences? All right, so now we have all of the theory. How do we make it actionable? And in a classic PM fashion, we will create a framework, a scoring framework, which will score each vector we've discussed on a scale of 1 to 5, given a problem or a task. 1 is a low fit, and 5 is a high fit for agentic systems. And the scenario that I'm using to apply this framework is route modification in inclement weather conditions. Walking through the 6 vectors in terms of accuracy and risk tolerance, the score I've assigned is 4 because the system will suggest alternate routes to avoid hazards like flooded roads or icy patches. Errors in routing are tolerable as long as safety critical tasks, example braking or even visibility, remain deterministic. Variability of the decision environment is going to be quite high. So, and we talked about how the more variable the environment, the more agentic systems, a properly configured agentic system will be useful. So I've given it a high score of 5 because it can adapt to sudden weather changes, such as roads becoming impassable due to snowfall. And in these scenarios, dynamic real-time synthesis of weather updates and traffic requires agentic flexibility. Autonomy and goal-directedness, I've given it a score of 3. It can reprioritize. It reprioritizes user preference, or it can reprioritize user preferences. Example, avoiding highways during severe weather. And goal modification is useful, but less critical than ensuring safe execution or a safe drive. Strategic reasoning, I've given it a score of 5, balances trade-offs between longer, safer routes and shorter, riskier ones, and evaluates trade-offs in real time under evolving constraints, which is, of course, a core strength of agentic systems. Learning and adaptation learns from past weather-related adjustments to proactively improve future recommendations. And then historical learning enhances performance, but isn't always essential for immediate decisions because extreme weather conditions can vary, are hyperlocal and can vary a lot. So the total score is 21 out of 25, which is a strong fit for an agentic system. Again, this is a starting point, and there are a lot of other questions to ask as well. And for each of these, we should ask more questions, especially comparison with deterministic systems. And then just to give sort of an idea of a threshold, like what score would be considered good or poor. This is just an unvalidated range and general guidance. If the score is 10 or below, the task that you're trying to do is relatively static, deterministic, and highly accuracy or safety driven. So probably don't consider an agentic system. And between 11 to 15, it's a moderate fit. 16 and above is a good fit. So you and your team can actually proceed with diving deeper into the nuances of the tasks and the data you have available, and whether you will create an agentic system from scratch or improve your current systems. So this is pretty much what I had to share today. But some parting notes. If you had to remember 3 things from this entire session, these will be it. Always ask at least these 3 questions. Given an intended outcome or a task, can we rely on semi-deterministic, probabilistic outputs for that task? Is it safe enough? Can a deterministic system do it without having to explicitly define every combination? And then the last one, can we augment our current systems, deterministic or otherwise, with generative capabilities or agentic systems? The next point is the objective and trade-off evaluation is where some of the most innovative product work will lie, at least in my humble opinion. Paul Graham says that the edge of knowledge is fractal. Objective and trade-off evaluation is one area where at least I didn't find a lot of literature, which is generally a good sign that there isn't a lot of practical applications or services yet, which means, again, this is ripe for innovation. And then the final one, trust will be at the center of all development, should be at the center of all development, because getting people and companies to trust autonomous agents will be one of the most important hurdles to clear for widespread adoption. So we, especially as product practitioners, have to keep trust at the center of all activities. Thanks again for being here. Thank you so much. You can find me on LinkedIn. My name is Puneet Kamal, and you have a good rest of your day and your week. Thank you.